Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to talk about Chapter 4, Chemical Bonding and Structure of the IB Chem SL curriculum. The first thing we're going to talk about in Chapter 4 is ionic bonds. So in an ionic bond, metals lose electrons and form positive ions, which we call cations, and nonmetals are going to gain electrons to form negative ions called anions. Now, this is all because we talked about this group right here being the noble gases and being the cool kids, and everyone wants to be like the cool kids, and that means you have 8 valence electrons. And so there's several different ways we can do this. If you're on this side of the table, a non-metal, you can gain electrons, and so these guys have to gain 1 electron, these have to gain 2, and these have to gain 3, and that's why you get these charges here. On this side of the table, it's going to be really hard to gain electrons to become like a cool kid. And so what they think is, hey, I can go backwards and become a cool kid. And so they're going to lose electrons. So this group needs to lose electrons to become like the cool kids. And this group needs to lose 2 electrons to become like the cool kids. And so therefore we get metals lose electrons to form these charges. And nonmetals gain electrons to form these charges. Now, generally, group 14, this is where carbon and silicon would be, do not form ions because it's really hard to either gain or lose 4 electrons. That's a lot of electrons to gain or lose. So generally, those are not going to form electrons. Now, the transition metals, which are the metals right here, they're a little bit different because this is when you start doing the D block. And when you get D block, you get varying levels of stability. And so there are different ions that they can form. And we'll get into this later, but you can represent the ion that they form with numerical symbols. A couple more things, just some little quirky trends. Aluminum is +3, and if you go down this kind of staircase right here, it goes down a charge each time. So this is +3, zinc is +2, and silver is +1. That's like a little trend that you should know there. And then there are these polyatomic ions. These are groups of atoms that come together to form ions, and they have varying charges here. Notice that these are not in the data booklet, and you will have to memorize these. Also, notice that if the charge is minus or +1, you do not write the number. So you don't write -1. You only write the number if it's greater than 1. Also, notice that the plus or the minus come after the number. So, you know, it's common to say +2, but it's actually a 2+ charge, a 4+, or a 2- charge, or a 3- charge, so on and so forth. Just some terminology there to keep you cool with the chemistry folks. So let's take a look at what an ionic bond actually is now that we've knocked out some terminology. So here's sodium and chlorine. Sodium has an atomic number of 11, chlorine has atomic number 17. This is what the electron configurations would be. We talked about that last time. This is what the Bohr models would be. Notice that sodium has 1 electron in its valence shell, in the third shell, and chlorine has 5 + 2, so that's 7 electrons in the valence shell. Remember that, so here we have the electron dot structure, and this just shows the valence electrons. And so sodium has 1, chlorine has 7. Notice that to be like a cool kid or have 8, sodium is going to want to give, piece of hair there, sodium wants to give chlorine his electron. And what this is going to do is sodium's going to give the electron here. Sodium's going to become positive, and chlorine is going to become negative. So now we have these 2 opposite charges, and we know that oppositely charged ions are going to attract each other. And so this is going to form an ionic bond, which is when oppositely charged ions are held together by electrostatic forces. That means positive being attracted to negative. This is going to form an ionic bond. Now, some components of an ionic bond. First off, we do not call this a molecule. Well, we'll talk about that more when we talk about covalent bonds, but this is not a molecule. Instead, we call this a formula unit. Okay? When these form, they form 3D crystals called an ionic lattice, and that's the and because of these 3D crystals, they've got very high melting and very high boiling point. It takes a lot of energy to break an ionic bond. It will, which is why most of them are going to be solids. You're going to have to add a lot of energy, a lot of heat to melt these into liquid form. They are soluble in water. Why is that? So we've talked about in class how water has a positive and a negative charge to it. Well, what that's going to do is it's going to kind of break apart. It's going to get in the middle of this positive and negative attraction with the negative oxygen mixing with the positive sodium and the positive hydrogens mixing with the negative chlorines. And it's going to get in the way of this ionic bond. So they're going to dissolve in water. Also, they conduct electricity when they're in liquid, either when they're melted or when they're dissolved in water. They're going to conduct electricity because these charges can move about. You cannot get electrocuted by pure distilled water. However, if that water has some salt in it, the water can now conduct electricity, and then you can get electrocuted if the water has some ions in it. Also, they're very brittle, meaning they can break easily. Now, to figure out if a ionic bond is going to be formed, you can figure this out by looking at the electronegativity difference. If it's 1.8 or more, and you can find these values in the data booklet, if it's 1.8 or more, we're going to say that it's going to form an ionic bond. So let's take a look at some examples, some example problems here. So first things first, if the anion or the second element ends in IDE, you're going to be able to find it in the periodic table, and we'll talk about that more later. Secondly, it's always going to be the cation first and then the anion second. It's always going to be the positive first and then the negative second. So let's take a look at lithium oxide. Lithium, if we look at our periodic table, has a charge of +1, and oxygen has a charge of -2. Now, we talked about this diagram here being, all they're doing is just transferring electrons, but electrons are never really leaving the system. And so therefore, this has to stay neutral. If it was neutral before, it should be neutral afterwards. Again, you have these positive charges and negative charges inside, but overall, it should be neutral. And so I need to make this so that this is neutral. Now, the way to do this is through the crisscross rule. The crisscross rule is going to work for every single time except for one exception, which I will show you in a sec. What the crisscross rule is, you take these charges and you turn them into subscripts for the opposite ion. So here we have a 2 and a 1, and I'm just going to crisscross these. So it's going to be Li2, the 2 here is going to go here, and the 1 here is going to go there. Now, one little thing, again, you do not write the 1. It is incorrect to write it like this. It has to be Li2O. So this is the crisscross rule here. Another example, potassium nitride. Again, IDE tells me that I can find it in the periodic table. And right here, -3. So K is +1. So potassium nitride right here. Again, crisscross rule, so the 3 will go with the K, and the 1 will go with the N. So K3N. Let me show you a case where the crisscross rule doesn't work. That happens here with magnesium oxide. Now, if I were to do the crisscross rule here, it would be Mg2O2. But the correct formula actually here is MgO, because you want it to be the lowest ratio possible. So the formula, the only time the crisscross rule doesn't work is if the charges are equal. And if the charges are equal, you know that's simple because it's just going to be a 1-to-1 formula unit ratio. Okay? Now, let's take a look at some more examples. Let's take a look at this one here. Calcium nitrate. Now notice that this one does not end in IDE, which means I cannot use the periodic table to figure out this charge. Where I am going to find this charge then is in my polyatomic ions list. Other than hydroxide, none of these are going to be ending in IDE. Okay, so since it's not IDE, I can find it in the periodic table, or sorry, in the polyatomic ions list. Nitrate is going to be NO3-. So calcium is +2, nitrate is -3. Crisscross rule here. Now notice that 2 is going to apply to the entire NO3 formula unit. And so I'm going to have to put parentheses around it to represent that. Let's try one more. Ammonium nitride. Now the nitride is different from nitrate. Don't confuse those. And since it's ending in IDE, I know this is the nitrogen in the periodic table. So nitride is going to be -3. Unfortunately, there's no rules to figure out the cation. Just know that this cation is a polyatomic ion, NH4. And so, NH4 is plus, N is -3. Crisscross rule, and I get NH4, 3, and minus. One last thing we must talk about are transition metals. Now, transition metals, turns out iron has 2 ions it can make. It can make a 2+ ion or a 3+ ion. Now, to figure this out, I know that the chlorine has to be -1. And since I have this formula here, and since this is -1, I know that I have to have this form of the ion to make sure that this is electrically neutral. This is Fe3 plus Cl minus. Now to write this out, I would do iron and then 3, because I'm using the 3+ version of the ion. And then I do chlorine, but the ionized version, remember, is IDE, chloride.